Okay, it's great to have Maryam Fazel give the next talk. She'll talk about online algorithms for budget allocation.
Hi everyone, and thanks a lot to the organizers of the workshop and of the program. So before I start, I say this is joint work with my former student, Reza El-Ghali, who is a postdoc now at Berkeley. And the second part of the talk is joint work with James Sanderson, a former postdoc who's now a professor at Monash University in Melbourne. Okay, so I'll be talking about online optimization algorithms of a certain kind. They arise in online resource allocation problems. So first of all, what do we mean by online? When I have an optimization problem, if all the data for the optimization problem is available from the start, that's an offline problem. In an online setting, we have a problem that we want to solve, but the data of the problem are arriving in a sequential manner. They arrive online. And this can be some coefficients either in the objective or in the constraints, or both. And so, for example, at some time t, there are some new coefficients in your problem that are revealed, and there is a new decision variable xt that your algorithm has to choose. And this variable that is chosen at time t cannot change later, so it remains fixed after that. And there's also budget constraints that couple the decisions across time. So this is really a resource allocation scenario. You have a limited resource. At every step of time, you're deciding how much of it to allocate to some new opportunity that has come along, and you keep going like that. And you have a limited budget. And the goal the goal is to propose algorithms for which we can guarantee good performance in the sense of a competitive ratio, which is the ratio of the objective value that the algorithm achieves divided by the best offline solution. That is the best offline sequence of decisions. The other thing that one can set up in these kind of problems is the sequence of inputs that arrive to the algorithm. What kind of a model do they have? You can assume they're adversarial, so the data incoming to the algorithm can be arranged in the worst possible order, for example, or you have no control over it. And that's what we look at in this talk. But there are also other models. For example, the data arriving to the problem can be stochastic in various senses. There are several popular models for that. For example, random permutation model, where the possible set of inputs is chosen by an adversary, but they arrive at a random order. There could be IID. They are coming from some distribution in IID fashion, or some other stochastic models. So there is work in this area also, and some of our ideas apply, but I won't talk about it in this talk. So unfortunately, the amount of statistics in the talk gets a little bit reduced when your input is adversarial and not stochastic. But still, we'll see there is some relevance to statistics. So actually, a typical problem and an iconic problem that kind of started this class of problems is called the AdWords problem. And this is a problem of allocating advertisers to websites. It's a problem that, for example, is solved by search engines like Google. So suppose you're Google, and you have a set of advertisers that have signed up for their ads being shown to the relevant query. And each of these advertisers have a fixed budget BI. So advertiser goes to Google AdWords page, and they actually say, I have this much daily budget or monthly budget or something like that, and I want my ads to be shown in response to queries. And then queries are the unknown input that arrive online. So Google has their advertisers lined up, and a query comes. Somebody searches for a word in the search engine, and among the advertisers, 3 of them, for example, in this case, bid on that query, saying that I will pay this amount if you show my ad for that query. So A11 is the amount that advertiser 1 bids on first query, and then the other 2 aren't bidding, and the last 2 are bidding, let's say, these values. And we arrange them in a diagonal matrix, but that becomes obvious later why we do that. Okay, so the algorithm now received this data, and then it has to make a decision. There are 2 versions of this problem. The original version is that the xt is an integer variable, so you have to assign only 1 advertiser. And suppose in this case the search engine chose number 5, so this is the first x1 variable that gets assigned. There's also a fractional version of this, but I'll talk actually mostly about the fractional version, but say something about the integer one later. But the original version of the AdWords problem is integer. So for our purposes, it doesn't matter much. Okay, the second query comes in. Again, 3 of the advertisers bid on it, and again, the algorithm assigns, and third one comes in. Again, the advertisers bid, and the algorithm has to decide which one to assign, and this goes on. So you end up with some kind of, in this case, a bipartite matching. But what's the objective? What did Google try to maximize over the course of these assignments? Well, so search engine wants to maximize its revenue, which is the summation of the revenue it derives from each of the advertisers. And that's denoted by this function psi I. The shape of this function is, if this axis shows how much resource or what is the total allocation to each advertiser I, which is actually this, it's the amount that they bid times the x where they actually got a non-zero value of x. So a summation of those over time. That's the total amount allocated to advertiser I. And then the search engine will make linear profit until the advertiser actually runs out of budget, after which there is basically revenue stays flat. Means that you're not making any other money, even if you show their ad any more than this. Okay, so that's a hard budget in that sense. Now the xt's have to sum up to 1 and have to be positive. And again, the integer version of the problem says they're 0 or 1. The fractional version of the problem just says this has to hold. So you can have a half-half, show 2 of the ads side by side, anything like that. Okay, so this is an online optimization problem of the kind that I will consider. That's the cost function. And these are the constraints on the x. And the x's are the variables that have to be decided by the algorithm as we go along. And the ATI are the data that is revealed as we go along. So let's look at a very general version of this problem, and that's what we will look at in this talk. Here's the offline problem. You want to maximize a function of a sum of affine function of all our variables. So variables are all xt, and time horizon is m. These are all finite time problems. So x1 through xm are the variables, and these x's live in Rn. They can be n-dimensional vectors. An affine mapping of them, but then everything is coupled with each other by this function psi. Then there are some local constraints like that, xt and ft. Ft just needs to be a convex set, but they don't matter too much. The main coupling is actually arising in the objective. So actually, if I want to write it a little bit more explicitly, the psi has to be a concave function. And it captures both revenue and budget the way I've written it here, but I can also write it more explicitly as a summation of two functions, one of which is modeling the revenue that's derived from the decisions, and the second one is the budget violation penalty. So this could be an indicator function, for example, that says this value cannot exceed b. FTs are some constraints on the x's. In the previous example we had, the FTs were simply the simplex, the probability simplex, and the h was that function that I showed. And the g is an indicator function. The only other assumption we need is that we need to assume these coefficients, here they're matrices, AT, are such that ATXT is a vector with non-negative entries for all t. This non-negativity is important, and it does hold in all of these resource allocation problems, or more generally what's known as packing problems. So what's online? The online version of this problem is the algorithm knows the psi function from the start, but that's all it knows, basically. Everything else, like the ATs and the FTs, can arrive online. You see an AT and FT, then you decide the XT, and that XT cannot be changed afterwards. Okay, is that clear? Set up? Another example of this, a general set of problems, are online packing linear programs. Those look like this. So they're linear program, linear objective, linear budget constraints, often together with simplex constraints on the variable, and with the special assumption that all the coefficients are non-negative, the C's and the A's. And of course, it can be written in our form. If we bring this guy up and penalize it with an indicator function, it will be in this joint psi form, if you want. So this comes up in online revenue management. We'll see an example of that right after. Online packing and covering problems. So it's been actually studied in several communities, both the OR, or operations research community, and also the CS theory community, and online e-commerce and online advertising and so on. Several communities have looked at it. The AdWords problem is a special case of online packing LP. What is online revenue management? This is a problem that is just a special case of that linear program. And this is the simplest case when n equals 1. So every xt is just a scalar variable between 0 and 1. And the way it works is, just for intuition, it's good to see what happens. So I'm an inventory owner, and I own 5 items in my inventory. And at time 1, a customer comes and makes an offer of a bundle of goods that they're going to buy. They say, for example, I want item 2, 1 unit of item 2, 1.5 units of item 3, and I will pay $100. So they basically request a bundle of goods, and they make a bid on how much they will pay. An algorithm has to decide whether to fill that order or partially fill it or not fill it. And then other orders come along, but the total budget of each item in the inventory is fixed. So that's the inventory problem. Okay, here's a statistical problem that is actually quite interesting. It's the well-known D-optimal experiment design problem, which is well-known in statistics, very well studied. However, this is the online version. So this is the problem. We want to basically choose a set of experiments that maximize various measures of information, for example, or minimize various measures of covariance of the error. In this case, it's the volume of the error. We'll see a little bit more. Yeah, here. Okay, setup is like this. You have an unknown vector W, and you have linear measurements of it given by these vectors AT, plus noise, where the noise is simple unit Gaussian. We observe these observations, and we just concatenate them after we observe a few of them, solve a least squares problem, and return the least squares estimate. The error covariance of the least squares estimator is this. And here I have added this small multiple of identity to avoid the fact that your experiments need to cover the whole space, basically. You need to be full rank, but let's assume we already have made it full rank. So the error covariance of the estimator is the inverse of these experiments that you pick. So each AT is a vector. AT transpose is a rank 1 matrix. And xt is the coefficient that says how, whether you picked it or not, or what weight you put on it. And the inverse of that is the error covariance. So you want to minimize the error. You can maximize, if you want, the volume of this. Right, so the optimal experiment design minimizes volume of error ellipsoid. And actually, we will see that it extends to other experiment design criteria as well, like A optimal and Peace criterion and so on. Okay, but in this case, let's look at the online version. So the offline problem is this: maximize log of width of multiple of identity plus summation of xt, at transpose. Xt is a decision variable. There is a budget for the xt's with some cost factor ct. Xt is between 0 and 1. So in this case, if I pick the teeth experiment, I'll have to pay at up to this ct cost. I incur that ct cost if I set the xt to 1. So the online setting is that these experiments, AT, are made available to the algorithm just one by one. You don't know what's going to come in the future. Okay, so that's online experiment design problem. And this problem hasn't really been looked at in this kind of online setting, but it has been studied, very, very well studied in the offline setting. So in this talk, I will mention first a couple of a generalization of the typical algorithms that people use in this case, which are primal dual algorithms. But I'll present them in kind of very general way. And then we show that the competitive ratio of these algorithms can be bounded. And that bound is actually a function of a geometric quantity of the problem, the original function that defines the problem, that psi function. And we can derive such a bound under an assumption on that psi function, which is a kind of diminishing return assumption. And then the most important part I want to talk about is that we can actually use convex optimization to design the right shape function to get the best competitive ratio, or improve the competitive ratio. And then there are some intricacies about how to do it for the matrix problem for the experiment design, that if there's time, I'll show you that as well. Okay, so we have an optimization problem. The first thing to do is to write down the dual. Here's a dual of that original problem. So the one that said maximize psi of AT xt subject to xt in ft. Here's the dual. We minimize over y. Y is the dual variable. Summation of sup over ft of this inner product, AT transpose y and x. So you're minimizing this over y minus conjugate of psi. And just to remind you what the conjugate is, because psi was a concave function, this is the concave conjugate. It's the opposite of the convex conjugate. So it's defined as the inf over u of the linear function minus the function value. In the convex case, it's the sup of the line minus the function. And it looks like this. So if this is your function in one dimension, the conjugate is the largest gap between the line and the function. And then you can also read it off by taking, if you're evaluating the conjugate function at y, you can find the line that has slope y and is tangent to your function, and then read off this value. This is the negative of the conjugate, the opposite. So that's the conjugate function. So dual problem has a nice form, so that's good. We can also write down the optimality conditions. The optimal solution of the problem, that is x1 through xm all optimal stars, and y star, the dual optimal variable, satisfy the following. These are exact optimality conditions of the problem. I'm assuming psi is differentiable. It generalizes to non-differentiable as well, but this is simpler. So xt's maximize these inner products where y is the optimal dual variable. The optimal dual variable satisfies this relation with the optimal x's, where this is the gradient of psi. And so that is good, but when we are in an online setting, we never have access to the exact dual variable. If I knew the dual variable, making decisions at each time step would have been easy, because I've received this coefficient. If I knew y star, I would just plug it in, solve this, and return the x star t. But we don't know y star. So the style of algorithms that are used are either usually a sequential type of approach or a simultaneous approach. The sequential approach, and we call it greedy because at each step it tries to do the best, is that at time t you're receiving the coefficients and the constraints, and you assign the primal variable given the best estimate of the dual variable you have so far. So that's y hat of t. So just based on the best set of, for example, prices for your items that you have determined so far. If you're in an inventory problem, this has the meaning of price. So you have some prices for your items, and you use those to judge whether the latest offer that came in is good or not. You make an assignment based on that. Then you go and update your dual variables. Then you update your feeling or what you think the correct prices for your items are. And you update that by evaluating the gradient of psi at how much has been assigned up to that time. And you use this in the next time step. So it's sequential because it updates the x, then updates the y. And one benefit of this algorithm is that it's very, very simple. It can scale to very large scale easily. Only needs one gradient evaluation. And another benefit is that if in a lot of examples this ft is the simplex, as we saw, it's just a probability simplex, then this assignment will always returns a 0-1 solution. So if you're really interested in integer solution, this automatically is generating integer solutions, which in some problems that's a big deal. Now, another thing one can do just based on looking at the optimality conditions is, well, first actually let's rewrite the sequential algorithm slightly differently because it makes an interesting connection to another area. So that's the algorithm again. Evaluating the gradient at the previous point can also be expressed like this. And this is nothing but just using the definition of the conjugate function plugged in. The conjugate of a smooth function and the gradient are related like this. So y hat t plus 1 also has this expression. It's the minimizer of some accumulated linear function regularized with the conjugate of psi. So if you look at this, you may think that, oh, that's similar to online learning. Problems that arise in online learning where, for example, you're getting examples, you're updating a classifier, they look exactly like this, with this kind of regularization, with a particular regularization. In particular, the FTRL algorithm, for example, that's used in online learning is a case of this. So our y update or our dual update is really like online learning. Also that if ft is a unique simplex, xt is integer, as I mentioned. So actually this is basically the only connection with online learning I can see. The rest is different. We don't really measure regret here, etc. But there is some usage we can make from this. And we'll see that later. So, okay, what are the things that people can do in such problems? This was just one choice of algorithm. You updated x, then you updated y. It's very natural to say, can't I update x and y together? Because I actually really want to solve the joint optimization problem. And you can do that because once you receive AT and FT, you can solve this min-max problem and assign the solution to both y and x together. So you can certainly do this. It's a convex problem. It's computationally much more costly than the previous one. but also has a better competitive ratio. So we will first analyze this one. So this is just solves this saddle point problem at every iteration and updates the variables x and y together. And actually, some known algorithms in the CS theory literature, for example, Bookbinder et al. 2014, can be viewed as a special case of this when applied to specific problems. They applied it to online linear programming, for example. And they call it a continuous update algorithm. It's not described this way, but it's equivalent. So, okay, so these are the class of algorithms. So what can we say about these algorithms? For these algorithms, first, this problem is actually, without any assumption, it's very hard to guarantee anything. But there's a key assumption that enables bounding the competitive ratio. And that is the following. It's a diminishing return assumption. And we can state it with respect to any general cone or ordering induced by a cone, where in the special case of AdWords and all the previous examples, except for the matrix one, that cone is just the positive orthant, and the ordering is just entry-wise ordering of the vectors. But for the matrix problem, it's going to be the PSD cone and the PSD ordering. But the diminishing return can be defined with respect to any cone. If u is bigger than v with respect to cone k, the gradient of my function is less than the gradient at the other point with respect to the dual cone. And it basically has the idea that as you increase the value, your slope decreases. So the returns diminish, or the slope goes down. Yeah, so that generalizes the notions of diminishing return that have been used. In the literature, this has been used mostly in discrete settings like submodular maximization and so on, not so much in continuous, but we can generalize it and we can use it for any cone. Okay, so if the psi function in the original problem satisfies diminishing return, satisfies this assumption, and it has to be concave, and let's assume it's also monotonically increasing, monotone. So this assumption is not critical. There is extension for non-monotone as well, but it's more complicated. But concave and dr are critical. So if the psi satisfies these assumptions, then the simultaneous update algorithm achieves a competitive ratio. So the value that is achieved by the algorithm divided by p star is always bigger than 1 over 1 minus alpha of psi, where alpha is this quantity. It's the smallest ratio of the conjugate of the function evaluated at the gradient divided by the function value. And so this quantity is actually some kind of a geometric curvature. I'll show you an example in the next slide. But so one can also give similar bounds for the sequential algorithm, but you will have another additive term in that case. Okay, what was that quantity? 1 over 1 minus alpha psi. What is alpha psi? In the one-dimensional case, it's easy to see what it is. If this is the psi function, alpha psi, so I can pick a point u0 and then look at the tangent line at u0, and then this value, this value is the conjugate evaluated at psi prime. So conjugate evaluated at gradient at u0 is just this, and divided by psi of u0 is divided by this length. And then take the minimum as you go along as you move along the u. So the minimum ratio between this offset and the function value. And this actually takes a value for monotone function is a value between 0 and minus 1. And in fact, it is 0 for a linear function, because linear function is just the value is just 0. The two things are that value is always 0. And the worst case it can have is minus 1 for that AdWords function, which was linear and then flat. That gives you minus 1. So these are the two extremes. The other functions can have various curvatures and be in between. So I'll skip the proof, but it really has two steps. One is that you bound some sort of a duality gap using the conjugate function at the very last evaluation of your dual variable. But then you need diminishing return for the next step to link whatever your algorithm achieves to the optimal. And one thing to observe is that for monotone functions, because the alpha psi is always bigger than minus 1, competitive ratio is bigger than or equal to 1/2, so that's good. For non-monotone, it's much more complicated and needs more assumptions to be able to bound or something. Now, one thing about this alpha psi and its role. We can gain some intuition by looking at a very simple example of what happens to the algorithm when you get these assignments sequentially. So So suppose this is the shape of your psi function, is linear and then completely flat, and you're getting this a1, and you decide to assign, you take that a1, so you're here now, you look at the slope at this point, it is 1. So in the next time step when you're making your decision, you're actually also going to take the next thing that comes in because the slope is still 1 and so on. But then, of course, when you hit this flat region, suddenly the slope is 0. So you lose a lot. So basically, this algorithm that used the slope of the original function to evaluate the dual variables is too aggressive, and it runs out of budget very quickly. So that's bad. But if the function looked like this, if it was very slow to much slower to increase, or another way is to say, as you're getting close to running out of budget, it decreases the slope. So it becomes more conservative as you get close to running out of budget, then it performs better. Sorry. So that suggests that perhaps I can use the original psi, but then modify it to some sort of optimal shape that gives me the best competitive ratio. But there are two things to consider. The more you smooth this function, especially smoothing the corners, the better. But then the further it gets from the original function, and you always want to judge the competitive ratio with respect to the original function. So we don't want to change it too much. So we need to find what's the balance between these two things. If I replace psi with some smooth version of it, what would happen to the algorithms? The sequential update will change like this. The only change in the sequential update is as if the regularizer in your dual update has changed. You use a better regularizer. And in the simultaneous update, the change happens here. Sorry. Sorry. So then the competitive ratio is going to look like this. It is again 1 over 1 minus a new alpha, which now depends on both the old function and the new function, and it's explicitly this thing. If psi s equals psi, this reduces to the previous alpha. But if psi s is different than psi, this captures both how much you're paying for changing your function and how much you will gain. So the good thing is now we can ask the question, can I actually optimize over the psi s and find what's the best smoothing for my problem? There is some relation to idea of smoothing and optimization. In fact, smoothing via conjugate functions has appeared in many places. It actually goes back to Bertsekos, early work of Bertsekos and Polyak. And often what they did was to try to find a smoother version of a function psi by adding something strongly concave to its conjugate and then take the conjugate back. So that's the typical recipe. However, you have to know what to add, and in many cases it's just a L2 norm squared, etc., a very simple function. But what if you're in a complicated situation, you don't know what to add? So in these online problems, actually it's critical what you are putting there, and you may not know what is suitable for each problem. So for example, for the AdWords problem, in fact, this was basically done in by Devanur and Jain in 2012. And they showed that a shifted entropy, a particular shifted entropy that can be used to smooth the function, they actually didn't say it that way. They just say we give you this algorithm, and it's actually equivalent to having smoothed it with a shifted entropy. That achieves the best competitive ratio of 1 minus 1 over E, and they also prove this is optimal for that problem. So that's very nice. And there are several other problems like the online linear program, online packing linear program, online covering program that have been studied also by Bookbinder and Naor, and similar best known competitive ratios are given. But our question is can we systematically pick this phi? Or can we systematically smooth the function psi? So if we assume that the psi is separable in each coordinate, that is, for example, true for the AdWords problem, then then we can actually design psi s by solving an optimization problem. And turns out this optimization problem is convex. It's infinite dimensional, so we have to discretize things, but it's convex. And the good thing is that this can be solved offline because it only uses psi s, not the data. But once you've solved it offline, then you run your algorithm using this optimized psi. So here's the optimization problem. We have replaced the psi s with the integral of another function y. So it's just change of variable. So y is now the new variable. Y needs to satisfy this, so continuous function with a domain of 0 and infinity. And it has to satisfy this inequality. So here the variables are y and alpha, and we want to maximize alpha. So this is actually linear in y, this is linear in alpha, and this is convex in y, so it's all good. It's convex. However, it's infinite dimensional. Both y is infinite dimensional, and we have infinite number of constraints, so it's semi-infinite. So it sounds terrible, but in one-dimensional case, it's not too bad to simply discretize it and also truncate the interval. We can show some concrete results about truncation of the interval. For AdWords problem, or for, in general, any function psi that flattens after some time, truncation has no error, does not lose anything. For other functions, it does lose some error, but at least numerically doesn't seem too bad. So here's one numerical example. This is very similar to AdWords, but only has two breakpoints instead of one. And this is the original function. And this is the blue one is the function that comes out of the optimization. It's quite different. It's not even close to the original, but it does turn out to give you the best competitive ratio. And this shows a plot of basically the phi function. If you wanted to compare it to this standard smoothing, like what is the equivalent phi function that I had added in that case numerically? And it turns out to be this. This is what was added to the conjugate, and it's not even concave. So it's interesting. This optimization problem doesn't require what you added to be concave. Just that the overall function has to be concave. So we don't know exactly why this happens, but turns out this is giving the best competitive ratio. And you can also compare it with something else, some other handcrafted solution, which is the following. People had already studied AdWords, and they know what the best algorithm is. And this problem is basically the summation of two AdWords, right? You can write it as this one and this one. And then you can say, I smooth each of these, or I apply the known AdWords results to each of these and add them up. But if you do that, you don't get your competitive ratio is not the best. So what we get numerically is still better than doing that. So we don't know what the true optimum is for the AdWords with two breakpoints, and that's not known. But it's cool that one can just solve an optimization problem and find something that optimizes the bound on the competitive ratio. So we're optimizing a bound on the competitive ratio, not a true competitive ratio, which we don't know, but still. So in a few minutes, I'll show you what happens with the matrix problem. Actually, let me first ask, is there any questions? Yeah.
The motivation for the second breakpoint is that, I don't know, somebody starts spending less after some point, or less, you know, interpret that.
It could be, let's see, so if it's an AdWords problem, that means that maybe Google starts to get less revenue with showing a particular advertiser's ads more and more. Like after some value, maybe they get less revenue. Or maybe they start to give them a discount. Like they did something, but they say, okay, I'll show you your ad for this. Something like that. I think in general, this kind of curve is common, at least in the revenue and economic setting, that you initially are steeper than later. It could be discount breakpoints and so on. But to be honest, I just made this up for the illustration. So. Okay, so so now for the matrix problem. This is a version of our old problem, but now these A's are matrices that are positive semi-definite, so they're in Sn plus. Positive semi-definite matrices. These are scalar C, and the X is scalar here. X is just a scalar between 0 and 1. And this problem is written as something that would cover all these experiment design criteria. And this G is the budget violation penalty. And if you want an exact hard budget, you should set it to be the indicator function. So it's 0 if U is less than B, if the variable is less than B, minus infinity if the variable is bigger than B. Okay, so if that's the problem, our psi function is this h and g together. And the g part in this case turns out to be easy to handle for the smoothing, but the h part is tricky. H here can be any trace function of a matrix. A trace function is a summation of scalar concave functions of the eigenvalues. So it's a summation of h of lambda I of the input matrix. So for example, it can be the log det of epsilon I plus u. That would then give us the online experiment design problem with the d optimal criteria. It could be negative trace of epsilon I plus u inverse. This is the a optimal criteria. And I think if you put minus p here, that's the piece mean criterion. And the experiment design, these ATs, the matrices here, are just this rank 1 outer product of the measurement vectors. So in this case, we need to find a smooth version of the H and a smooth version of the G. And for the H, we need to ensure it satisfies the diminishing return property. In the previous example, when we assumed that the function separated to a summation of one-dimensional functions, diminishing return is the same as concave. In 1D, they're the same. But if you go to something more complicated like here, diminishing return actually says a lot more than just being concave. So we need to find a function that has that's a complicated function of eigenvalues and has diminishing return. And the goal is to maximize the competitive ratio, minimize budget violation. So if we combine the revenue and the budget violation penalty, then we are balancing the two. We can pick some parameter gamma to capture the trade-off between these. So then the design problem becomes something like this, a bit complicated, but the point is similar to before. You can do a change of variables to basically optimize over the derivative of this h function, over this y. And the first constraint is very similar to what we had before. This basically guarantees the competitive ratio because this is the conjugate of the gradient divided by function value over here, and that gives you and this beta is the competitive ratio bound. So that's the same as before. This gamma was just a trade-off parameter that we pick ourselves. But one thing that's new here is that what are matrix functions or trace functions of matrices that satisfy diminishing return, and is there a representation for such class of functions? And luckily, the answer is yes, and it's available just by using Lohner's theorem. Lohner's theorem on monotone operators enforces the R and says basically any monotone operator on the PSD cone can be represented by such a function. So the function itself is summation of h of eigenvalues, and the h is the integral of y, where the y has this integral representation with respect to some measure on 0, 1, mu. And it's very deep stuff, but it just comes out of Lohner's theorem. So this is good because it enables us to optimize over these. If we did not have such a representation, our observation before that to optimize to find the best design would not have worked. So let me just skip the details. One can do this. So for example, this is for the d-optimal experiment design. The little h function will be log of u plus 1. And the original budget function is going to be 0, and then the budget here was 100, so then minus infinity. This budget function gets smoothed to either of these curves. This depends on the value of the gamma. So if you pick gamma 1, you get the green curve, gamma 2, this one. And gamma is basically telling you how much you really want to enforce the budget. So the larger the gamma, the more you're enforcing the budget. So that's for the G. And the H, the original H given was like this. This is the log of 1 plus u. But after optimization, we get this blue curve. And this is actually the corresponding measure mu of lambda. We have discretized lambda, but we discretize it very finely between 0 and 1. And I have no interpretation of this. It's kind of weird and interesting, but that comes out of the numerical solutions. We tried many examples, and the measure actually has many different forms. Sometimes it's kind of atomic, only picks a few non-zero terms, but sometimes it's spread out, like this one. So we don't yet know why it's doing what it's doing. And we can also show trade-offs between the competitive ratio. So this one has a competitive ratio here, the bound on competitive ratio, versus gamma, the trade-off parameter. So the larger the gamma, the less you violate the budget, but the lower your competitive ratio. So you're trading off those. And this is also budget violation versus the trade-off parameter. And this just shows that different choices of other parameters don't really change the curve very much, simply scales it. these are actually for another experiment design problem which corresponded to A-optimal experiment design. One thing that's interesting about A-optimal experiment design is that this function is not diminishing return itself, the original function. But when you smooth it, you're imposing diminishing return property. So it's as if you're approximating the original function with one that has diminishing return. So this can be used even if your original function did not have diminishing return. The log death penalty does have diminishing return, but A-optimal one does not. And so, yeah, I have almost out of time. So there's some more related literature. I think I mentioned all of these, the online linear programming mostly from the CS theory literature. And relation to regret to some extent has been pointed out in some of these works and also in our work. But the only relation is really through the dual. The dual updates in this style of algorithms are very similar to FTRL algorithms in online learning. So potentially there's more connection there to be explored. And summary and some references. Thank you. Yep.
I might have missed it. So is this all for a fixed finite horizon?
Yes.
And the competitive ratio is at the end of that horizon,
Yes.
or any time?
At the end. So
And
we are
are they
comparing to
greedy
the
out?
offline problem that has the full information up
Yeah.
until the end of the horizon.
But some of those algorithms seem kind of greedy, I guess. And I'm just wondering, can you say anything about, like, do we stop at some earlier point just because they're purely greedy anyway? I mean, they didn't seem to be too operationally thinking about the horizon.
Yeah, I see. Yes, because this is adversarial, you can't really even use horizon information.
Right.
Even if you know M, algorithm knows M, knows the horizon, but it doesn't help it because the adversary can stop at any time they want before M. So actual stopping time can be even before M. So for these worst case algorithms, knowledge of horizon or remaining time on the horizon doesn't really help. But actually, if you have stochastic inputs, that does help. You should actually take into account. So you can change your strategy whether you're early in the horizon or late. So yeah, algorithms that have random inputs or random permutation inputs actually use that.
I'm not sure monotonicity, but the competitive ratio is getting monotonically worse as the horizon's getting bigger, something like that. Yeah, I mean, in light of this question.
For adversarial input, I mean, your adversary can cut your horizon at any time, so you can't really.
And there's only more freedom for your adversary as you grow the horizon. So that translate into worse and worse competitive ratio. Generic.
So you're asking if the horizon increases and we run the same algorithm, and the algorithm knows the horizon, right?
Yeah, exactly.
Yeah. Does the competitive ratio get worse?
Yeah, as you grow the horizon. Maybe it's not clear.
It's not clear. I don't know, actually. Because what can the algorithm do? I mean, it knows that it has to end before that horizon. So, and the adversary might end it earlier. So you don't actually know you have that much time or not as the algorithm. All you know is that I have one more step, something like that. But knowing that potentially you can have a longer one, I don't know if that helps the algorithm much.
Probably not, yeah. Maybe it's possible to show that.
But in the random input setting, it definitely does.
Yeah. So for the random input setting, are the algorithms, do they look substantially different, or does the same sort of regularized algorithm work well for regret?
The ones I have seen are still greedy, but they do use the horizon information. So how much time left affects the slope, for example. So as you're getting closer to time running out or budget running out, you're balancing both. But here it was really, they were just measuring how much budget is left, because that's the thing they know for sure.
Any other questions? Good, well, let's thank Maryam again.
Thank you.